In this video, I want to look at connections between the orders of elements and the cyclic subgroups that are generated by those elements. So to start with, we are going to let A be an element of G, and we're going to assume that the order of A is equal to K. So the question is, what can we say about, and let's actually write this down. What can we say about the cyclic subgroup generated by A under these circumstances? Well, I want to think about what I actually know under these hypotheses. I know that A to the K is equal to E, and I also know that A to the L is not equal to E if L is bigger than or equal to 1 and certainly strictly less than K, because that's the definition of order of an element. Now what I'm going to do is I'm going to let S be the set E, A squared, A cubed, all the way up to A K minus 1. And what I want to make a note of here is that E is equal to A to the 0, but it's also equal to A to the K. And as a consequence, there are K things on the list of elements for S. And I kind of want to make an observation. The list for S certainly contains K items. The question is, are those items all distinct from each other? So, are these items all distinct? Because I want to know whether or not there are any duplicates on my list. So in other words, what this particular thing is saying is, does my list have duplicates? So what I want to do is I want to investigate that particular idea. So the set S looks like this: E, A squared, all the way up to A K minus 1. And I claim that there are no duplicates. And what that means is that I am claiming that S actually has exactly K elements in it. So to prove this claim, I want to do a proof by contradiction. So the proof is going to be, let's suppose, by way of contradiction, that S has fewer than K elements. In other words, we have duplicates. So there is a pair of duplicates. Now, what does that really mean? That means the following things. We have an A raised to the I is equal to an A raised to the J, where we can assume the following things. 1 is less than or equal to I, and I is going to be strictly less than J, and J is less than or equal to K minus 1. In other words, these two things are somewhere on that list up here. And to kind of put them in, we have an AI and we have an AJ, and these two guys we are assuming are duplicates of each other. That's what's going on. Now, it's important to realize that this particular equation is an equation inside the group G. And because it's inside group G, we can take that equation and we can manipulate it, and we can do the following things. Since we know that AI is equal to a to the j inside group G, we have, by pre-multiplying by AI's inverse, we get AI inverse times a to the I is going to be a to the I's inverse times a to the j. And now we know how exponent rules work, so I kind of want to recall that a to the i's inverse is a to the minus I by exponent rules. So our equation now boils down to a to the minus I times a to the I is equal to a to the minus I times a to the j. But again, I know how to deal with exponents. In a group, a to the minus I times a to the I is just going to be the group identity. And on this side, this is going to be a to the minus I plus j. But minus I plus j is the same thing as a to the j minus I. And I claim that this is a contradiction. And I want to carefully explain why it is a contradiction to the fact that the order of A is equal to K. So let's explain that very, very clearly. We already know, this was our main hypothesis, that the order of A is equal to K. So A to the anything is not equal to E if that anything is smaller but bigger than or equal to 1. We also know that E is equal to a to the j minus I, and we had 1 is less than or equal to I, which was less than j, which is less than or equal to k minus 1, which was certainly less than k. And that's enough to imply that j minus I is going to be at least as big as 1 because I is smaller than j, and it's got to be smaller than k minus 1, which is smaller than k. So we have something that if L is equal to j minus I, then L satisfies this equation, and that would mean a to the L should not be equal to E, but it is. So that's where our contradiction comes from, and the only way out is that we can conclude that our additional assumption that S had duplicates is wrong. In other words, we can assume that this particular set has no duplicates on it. So there are no duplicate elements. And what that means is S has exactly k elements. Now, the importance of this is not the set S itself, but the fact that we get the following important theorem. And this theorem is stated as follows. We're going to let A be an element of group G, and the order of A is equal to K. Then it turns out that the cyclic subgroup generated by A just happens to be the set that we've been looking at, E, A squared, all the way up to a to the k minus 1. In other words, the set S from the previous stuff. And I do need to make my notation a bit clearer there. So what I want to do is I want to think about how are we going to prove this important theorem. Well, the proof of this theorem is not as difficult as the proof of the claim about set S was. The first thing is I want to, let's let S be this set. The second thing is I want to note that this set here, by definition, is all of the integer powers of A, so it can be written as a to the n, where n is any integer, so it's the set of those guys. So very clearly, S is inside the cyclic subgroup generated by A. We need to show that the cyclic subgroup turns out to be a subset of S. Because if we can do that, then we can conclude by a double inclusion that the two sets are exactly the same. So what are we going to do? Well, let's let B be any element of the cyclic subgroup generated by A. Then I know B is equal to A to the n for some n inside the set of integers. I also know that k is a positive integer. And that's important because the division algorithm now says there exists q and r such that n is equal to q times k plus r, and 0 is less than or equal to r, which is less than k. Now, what I'm going to do is I'm now simply going to use this fact to rewrite B in a way that is useful. So look at this. B is equal to a to the n, and a to the n is a to the qk plus r, but exponent rules say that that's going to be a to the qk times a to the r. And a to the qk can be written as a to the k raised to the q times ar. But a to the k is just e, so that's going to be e to the q times ar, and that's going to be a to the r. And I want to justify each of these things very briefly. This is the division algorithm. This equality is exponent rules in groups. This is more exponent rules in groups. This equal sign is the fact that the order of A is known to be k, so A to the k is equal to E. And this last one is basically the definition of E. E to the q is going to be E, and we know that E times A is equal to, well, A to the R is equal to A to the R because of the definition of E. So what we have on this particular set of calculations is the fact that B inside the cyclic subgroup generated by A implies that B is actually equal to A to the R, where R satisfies that particular inequality up there. So A to the R definitely is in my list of E, which is A to the 0, A to the 1, A to the 2, all the way up to A to the k minus 1. And so what does that mean? That says if B is inside the cyclic subgroup generated by A, then B equals AR is inside that set S. So the cyclic subgroup is indeed a subset of S, and since we've already observed that S is a subset of the cyclic subgroup, that implies the cyclic subgroup is actually equal to S. Well, what this means is that we can refine how we've stated this theorem as follows. So I'm going to restate our theorem. If A is inside G and the order of A is equal to K, then the cyclic subgroup generated by A is going to be the set E, A squared, all the way up to A to the k minus 1, and the cyclic subgroup has exactly k elements in it. In other words, the order of a group tells us, the order of an element tells us how many elements are in the cyclic subgroup generated by that element.